All right, here we go. So we're going to keep going with integration here. We've been doing a lot of geometry, so we're going to mix it up and do some algebra now, get back into algebra land. And let's start with a velocity function. So we've been doing this for a while. Remember, velocity is just the first derivative. And a lot of times, we have the velocity, but we want to find the acceleration of something. So we just take the derivative, yeah? So easy peasy. This is a nice friendly one. We get what? 2t minus 6. So we're good at taking the derivative. So if I have f prime, I can find f double prime. The key is, what if I want the original function, or in this case, what if I want that position function? A lot of time we need that position function. Wouldn't it be nice if we could go backwards instead of taking the derivative? Like maybe we could take the antiderivative. Oh, boom, there it is. That's what we're going to do. We're going to take the antiderivative. Maybe you can do this one in your head, and then I'm going to show you some rules for it. But let's think about it. I could take the derivative to get this. Could I go backwards? Can I turn the velocity into the position function? Well, we know the power rule. You drop a power, blah, blah, blah. Let's try it the opposite way. So if I have t squared, what do you think is going to be in my position function? Well, it's got to be t cubed, right? You've got to be 1 bigger because you're going to drop a power. The problem with this is I need a 1 in front, so whatever you bump this up 1, you're going to divide by that number. So you're going to divide by 3 in this case. So if I took the derivative of this, I'm going to get t squared. How about the next one? I'm going to take normal t, bump it up to t squared, and it was 6. And then what am I going to do? I'm going to divide that by 2. Pretty amazing. How about the next one? What is a 2 going to turn into? 2 is going to turn into 2t. So I just bumped it up 1. You could say you divide it by 1, but nobody divides by 1 anymore. We don't need to do that. And then also there could have been some constant here. So don't forget about this. We always are going to put a c on there, some kind of constant. So we can find antiderivatives. There it is right there. And we can clean that up a little bit, can't we? Sure, we can say 6 divided by 2. Really, this looks funky to me, like saying t over 3. I would say it's 1/3 t cubed. This is much friendlier for me to just wrap my brain around. I just prefer that. 6 divided by 2 is the 3t squared. And then I had the 2t plus the c. So in my mind, that's a better way to write the position function. That's how we're going to do it. And you can double check it. 3 times 1/3 is 1t squared. 2 times 3 is 6, blah, blah, blah. Do this one, you get the 2, and then we get a constant that just disappeared. That's what this whole section on is, finding antiderivative. So fun. I love it. So let's do the antiderivative. So I have f prime. I want to find f. That's my goal. So I'm going to go ahead and do the times it by, I'm going to bump it up 1. So that's the rule. We're going to bump it up to 4. Then I'm going to divide by 4. So this will be 2 divided by 4. I'm going to write it out in front. I just have better luck with that. You can write the whole thing over 4 if you prefer. No worries there. Same thing here. I start with the variable which was x to the 1. I'm going to bump it up to 2. Whatever you bump it up to is what you're dividing by. This had no x, so it'll be 7x. And then don't forget this c out here. It's some constant. Whatever that number is, I don't know. It's going to disappear. Maybe it was 100. Boom, it's gone when you take the derivative. So don't forget about c. Hugely important right there. Can I clean this up a little bit? Sure, I can clean that up. 2/4 is just a half. 5/2 doesn't reduce, so I'm going to leave it alone. And that's basic. That's all I can do. That wasn't very exciting. Sorry, I should have a little more excitement there in that one. But that's the antiderivative of that one. Excellent. So what if I have a super long one here? Let's still do it. We got the antiderivative. Bump it up 1 to 5, and you're going to 1/5 it. What do I do with x cubed? I'm going to minus x cubed, bumps up to x to the 4th. Divide by that. This will be 3/4. Take the x squared, bump it up to x cubed, and I'm going to divide by that. Hopefully you're getting the pattern here. I'm just going to keep this train rolling. Bump that up to x squared. Divide it by that too. Don't forget, any constant will get an x, and then don't forget about our friend little c here. Barely made it in that space, but we got it. We got in there. Hopefully you got the pattern now. Got the pattern going on. So let's do a little bit trickier. Sometimes you got to rewrite it. Remember we had to rewrite to take derivatives? I like to think of this as 1/2. So I rewrote it. Now I'm going to go ahead and take the antiderivative. So I'm going to bump that up. What does that bump up to? It bumps up, if you add 1 to 1/2, you get 1.5 or 3/2. That looks terrible. Let's try it again. You get 3/2. And I'm going to divide by 3/2. But remember, when you divide by 3/2, I mean, you can write it like this. Divide it by 3/2. That's really weird. Dividing by 3/2 is really what? It's multiplying by 2/3. So you're going to multiply it by 2/3. So flip that fraction and multiply. It'd just be the same as if you had 1 divided by 3/2. You flip the second fraction and multiply. Awesome. Don't forget to give you that 4x right there. This is my function, so I had the derivative plus c. All day we can antiderivatate. That doesn't sound right. Take the antiderivative all day long. Let's write a rule for this. So if I have the integral, if I'm going to integrate something or take the antiderivative of any x to the n, what am I doing here? Well, you are bumping x up 1 to the n plus 1, and then what are you doing? Out front here, you're saying 1 over that bumped up number. And you always have to add this c. So this is the basic rule. This is like the opposite of the power rule. Because of the power rule, we can do this rule right here for integration. Excellent. Let's apply it to some other stuff here and get some vocab. So we've always talked about definite integrals. They were defined. I would say find the area between 1 and 4. You know, I always had an a and a b. No more. Sometimes we have an indefinite integral, so it's just open-ended. So if I have a function and I want to take the antiderivative, we're going to use this. We're going to say the antiderivative of this is capital F of x. So that big capital F means what? Well, if I took the derivative of that capital, what would I get? I get little f. There you go. So it's the antiderivative. So the antiderivative of f is capital F. So that's some notation we're going to use a lot in this section coming up. We're getting there. It's all building up to something pretty exciting. So can I evaluate these indefinite integrals? Sure. It's the same thing we were just doing. This is another way of saying find the antiderivative. So if I want to evaluate this, 9 turns into 9x. I bump that 2 up to a 3, divide by that number, plus a c. Evaluated. Done. Got it. Awesome. How about this? So I kind of mixed up some special cases here. I know you may be getting tired of the pattern, but here's some special cases. So I can do a little rewrite here. I'm going to rewrite. I really want the integral of 6. Whoa, I don't want the 6 up there. Let's try that again. I want 6. What is that? That's x to the negative 2. And we'll leave that as a negative. So I can do negative exponents. I have not addressed that yet, but it follows the same rules. What am I going to do? I'm going to bump negative 2 bumps up to negative 1. I'm going to come out here and divide this by negative 1. Excellent. I've got x to the negative 3, bump it up to the negative 2. Come out here and divide by negative 2. This looks terrible. It's right. Oh, wait, no, it's not right. Now it's right. That's what right looks like. Add the c in there. But nobody, let's clean this up. We got, what is this? This is really negative 6. I can put the exponent back on the bottom because it's negative 1. A negative negative is a positive. Move that exponent back to the bottom. This will be 2x squared, and then I got my c. So that looks much better. So sometimes you got to rewrite it and then put it back when you're done. Excellent. How about this bad boy over here? This looks terrible. This looks like something I do not want to integrate. But if you split this into fractions, just like we did with derivatives, remember sometimes we'd have this? You can make this 3 different fractions. It's the same thing. We're just separating our fractions, and now we can integrate that. So if I integrate that, well, we should probably simplify it. Let's break it down. So my x's cancel. I get 2x squared. Then I get one of the, this cancels one of those. This cancels one of those. So I get 4x. And then the x's cancel here. And now this is a plain old polynomial, just like we've been doing. Let's just finish it out so we have it. I like to have a little closure here. Bump it up and divide by it. Woo! And bump it up. Divide. 4 divided by, I'm going to go ahead and just 4 divided by 2 is 2. Bump it up. Add the c. Bump it up. I like that. Excellent. There it is right there. So we've got indefinite integrals. So really, we're just not defining them. All right, so here we go. Let's take a look at some definite integrals, and this brings us to the fundamental theorem of calculus. This is huge. A little note here, anytime you see the word fundamental with something, it's kind of a big deal. So fundamental theorem of calculus, sometimes you see it as FTC, is pretty important. So you're going to see this again. This is kind of why we do calculus. Is a huge, the fundamental of calculus. So what is it? Basically, you can read through the formal definition here, but the idea is if I have a continuous function on a closed interval, and remember the definite integrals from a to b, the lower bound, the upper bound, I can evaluate this algebraically. I can actually come up with the answer algebraically. Before we were using the calculator or the geometry, we're using the shapes underneath. So what do? Well, you just take the antiderivative, so capital F of b minus the capital F when you put a in there. It's so easy. It's just that. You would think, wow, it's got to be bigger than that. Nope, that's it. That is the fundamental theorem of calculus. So cool. We're not going to really prove it so much as use it. So let's go ahead and do one. So the first thing I'm going to do, I want to evaluate this integral. So what am I going to do? I'm going to go ahead and take the antiderivative. First step, find the antiderivative. So I'm going to say, okay, bump up the x squared to x cubed, divide by 3. Well, it was 3, so that's gone. That's just 1. Plus I have x, so that's going to bump up to x squared, divide by that 2, so I got 1/2, and bump up my x. Now you'll notice now we don't have a c. We're not too worried about the c. Let's put the c in for the first time. Sorry, this is our first time doing it. We better put the c in there. But something cool is going to happen. So when I go to evaluate this, you can use this bracket like this. I'm evaluating the integral from 2 to 6. Some people use just a straight line here, and some people close the bracket on the other end. It's just a personal preference, however you want to do it. I'm going to use the one-sided bracket just for now. This is I'm going to evaluate this from 2 to 6. So I want the f of b. So remember, it's from a to b. So I'm going to say put 6 in there. So really, I'm looking at what? I always use brackets for this part. I'm going to say it's 6 cubed, put it in for x, plus 1/2 6 squared, minus 2 times the 6, plus some constant that I don't really know what that is. Now, what am I going to do? I'm going to subtract the f of a. What's the f of a? Well, that means put 2 in there. So go wherever there's an x, replace it with a, which is 2. So I'm going to replace this with 2, minus this 2 times 2, plus that c. And there, I'm going to subtract these two things. So let's clean this up a little bit. 6 times 6 times 6, I believe, is 216. Plus 36, half of 36 is 18. Minus, is it 12? Plus some constant here. And again, this is all going to subtract this thing over here. And what happens when I cube 3? I get 8. Plus half of 4 is 2. Minus 4 plus some constant. And let's see if we can clean this all up here. 18 minus 12 is 6. So I'm looking at 222 minus c is my first bracket. That's the f of b. Minus, what do I get here? 8 plus 2 is 10, minus 4 is 6, plus c. So now I can evaluate this. What do I need to do? I can distribute that negative. So if I distribute the negative, you know what's going to happen here. Oh, why do I have a negative c? Oops, sorry, that was not supposed to be a negative c. So it was plus c there. All right, so when I distribute the negative, what's going to happen? I've got this 222 plus c minus 6 minus c. What's going to happen? Your constants are going to cancel. Whatever that constant was is going to cancel out. So it doesn't even matter. What matters is this 222 minus 6, which gets us what? Back to what? That's going to equal 216. That is awesome. That is super cool. That is doing it algebraically. Do you believe me? Yeah, I hope so. But if you don't, I'm not worried about it. You can check it. You can say, Mr. Bruss, I want to make sure. So let's just real quick do a math integrate and see what we get. You know, if I'm going to double check it, make sure this fundamental theorem of calculus works. Plug that in the calculator, double check it, and what does it come up with? 216. That's awesome. The calculator agrees. So hopefully you're happy. You believe me now without the proof. Awesome. Let's do some of these. Let's do another one. And from now on, I'm not going to include that c. No need for that constant because it cancels every single time. So let's just do it. I'm going to first integrate. And if you want to pause and work ahead of me, that's cool too. Bump this if you like. Just going with me. That's cool. Bump it up, divide, that's going to turn into 3. And then I'm going to evaluate from negative 2 to 5. Notice I did not put c in there. It's going to cancel. We just don't waste time writing it. So first bracket, we are going to go 4 times 5 minus 3 times 5 squared is the first part. That's the f of b minus the f of a. We've got that negative 2 we're going to evaluate in here. These are kind of fun. And we're going to say what? This is going to be 20 minus, 75 is my first part, the f of b. And if I evaluate this, it looks like I get negative 8. And that's 4 times 3 is 12. So we're looking at negative 55 minus, what is this? We've got a negative 20. So if I do minus a negative means add them, I'm looking at negative 35. So again, remember integrals can be negative. The area of the curve is always positive, but when we integrate, we can definitely get negative numbers like we just did. Awesome. That is the fundamental theorem of calculus. Let's wrap it up with some special cases, some things, we don't really have a rule for absolute values. You just got to think about them. I know you probably love that answer. So if I want to integrate an absolute value, well, if you think about it, this is an absolute value shifted right to. So we know absolute values look like these v's, and it looks like this. So you can just kind of sketch one and think about what's going on. But basically, there's going to be this axis of symmetry where it divides it in half. If you want to think about this as two different lines, like yes, from 2 on, this line is what? It is just x minus 2. But what is it coming in? My line is not straight. I hope your line is way better than that. Let's just make it thicker. There we go. That looks better. Make it a little wider. So what's the slope of that line? Well, it turns out this has got a slope of what? Down 1 over 1. It's what? It's actually just put a negative in front. And what does that really do? If you want, that means it is negative x plus 2. But basically, you take the absolute value. At some point, you're just going to throw a negative in front of the whole thing. So if I want to think of this as two integrals, I can. So if I want to go from 0 to 3, I'm trying to find basically from 0 to 3. That's what I'm trying to find. So in my mind, what I would do is, let me change colors here. You could say from 0 to 2, it's this first function. It's this negative x minus 2 dx plus from 2 to 3 of the other function, this whole x minus 2 dx. Now, is this something I can integrate? Sure, this is something I can do now, and I can find this. Would I do all that? Probably no. I'm too lazy to crunch all that. I'm just going to say the area. This is a 1/2 base times height, so 1/2 of 4. I know that's going to be 2. I know this is base and height's 1 by 1, and that's going to be a half. I know this is going to be 2.5. So I would do this one geometric if I can. So absolute value, you may have to do a little work, make a little sketch, come up with two functions, and those are our properties. Those properties are coming into play now. How about this if I give you a picture? Now I am talking area under the curve, so I do want to make sure I get just positives here. Luckily, this is all above the x-axis, so I'm coolio. I can say, hey, what's the area under the curve? This is a piecewise function. So from 0 to 1 is this function, from 1 to 2 is this function. So let's just set it up. I'm going to say, what, from 0 to 1, I have x squared dx. And what am I going to add to it? Just like the 1, I'm going to say from 1 to 2, I have this 2 minus x dx. And now these are things I can take and integrate and just add together. So all right, let's solve this guy out here. So we got this integral plus this integral, so let's do it. So let's first integrate x squared. X squared turns into x cubed, and I'm going to divide by that 3, and I'm going to do this from 0 to 1. So that's the first integral, and I'm going to add that to the second integral. Let me change colors so we don't get too confused here what's going on. If I integrate this, it turns into 2x minus that x turns into x squared, divide by that 2, and I'm doing that from 1 to 2. So I'm going to keep the first one here in red, keep that going. Let's evaluate. I love putting 1 in there. 1's great. Put that 1 in there. I could cube that all day. That's my first term. Minus, the only thing better than putting 1 in is, you guessed it, putting 0 in. Look at that. That is awesome. So it's really nice to put that in for the first one. And let's go ahead and just finish it out because we're dealing with this problem. So 1/3 times 1 cubed, that's just the 1. This is all 0. So the first part of this whole first part is just 1/3. So I've got it right here. I'm going to add that. So let's kind of show my work. I'm going to add it to whatever happens here in the green. Green's not as friendly. We're going to have to do a little work here. So the first one would be, the f of b will be 2 times 2 minus 1/2 of 2 squared. Plug that in. Minus, put 1 in. So there we go. I like the 1. So we got this thing going on. Plug that in. And if you want to think about this really, we could add another set of brackets or parentheses. I'm going to do all of this first before I add it to it. So I'm going to actually evaluate. So I kind of think of them as separate things and just add them all together at the end. So if I do this, I get 4 minus half of 4. So 4 minus half of 4 is 4 minus 2. Then come over here. It looks like I get 2 minus a half. So 2 minus that half is 1.5 or 3/2. And again, now it's really important that we don't do order of operations. I got to finish Greenie out over here. Don't give up on Greenie. So if we get a common denominator, this is going to be half 2 minus 1.5 is 1/2. So it looks like I've got, oh gosh, I messed up the colors. Let's try it again. Keep this color coordinated here. So we got the 1/2 on the right side. We've got the 1/3 on that side. Let's put it all together. And if we do a common denominator here, we're looking at what? 2/6 plus 3/6 is going to give me what? The area of that is 5/6 units squared. So I don't know, it doesn't tell me feet or centimeters or inches, anything on here, so I'm just going to go units squared when I label the area of that bad boy. So the first one was can't see that. Let's try it again. The first one was a third. The second chunk is a half. I integrated 2 separate times. That was lots of fun. That's a fun problem. How about one more of these? This time, some of them I just want you to set up and don't worry about integrating, because integrating can get pretty intense when we get a little later on. We're going to keep it pretty basic this section. But the idea of we got a piecewise again from here to here. So from 0 to 2 this time, I'm looking at this function negative x minus 1 squared dx. And what am I going to add to that? I'm going to add to this from 2 to 3 the other function, x minus 3 squared plus 1 dx. But be careful. What if I integrate this? What's going to happen? When I integrate this, I'm going to get a negative answer. Do I want a negative answer? No. So what you really need to do here is you need to absolute value this. So I want the absolute value of this. I want the positive. So go ahead and integrate and get this, but it's going to give you like -4, let's say. I want to absolute value it or subtract it. Subtract the negative and make it positive. Somehow I want to make sure it's only positive. Or some people you could do this. You could put the absolute value inside here. Ooh, I like this. We could do x minus 3 squared plus 1. Absolute value there. You can put outside, inside, I don't care, but I want that to be a positive answer. And essentially you're flipping it over the curve and getting that. All right, that's it right there. Go ahead and do some antiderivatives. Integrate these. Fundamental Theorem of Calculus. Love it. Good luck on the magic check. Peace out.